their token earnings to the content creator. And as an industry benchmark, we have Twitch on the very right-hand side in purple. They're at 95 minutes per user. So I want to show this to you because I think it really demonstrates solid evidence, right? Metrics that show the value of having this token on top of our protocol. And this really does increase user retention, user engagement to the tune of 2.5 to 3x compared to our previous metrics and definitely compared to Twitch as well. So now that I've given kind of an overview, a high-level overview of what we are, the problem space we're addressing, this is a blockchain developer conference. So I want to double-click now into some of the technical features of our blockchain. So, like I mentioned, we have the first layer, which is a mesh streaming layer, the data delivery layer, and then we have that built on top of the blockchain. And what that allows us to do is basically we're able to append one microtransaction with one micro payment. So a microtransaction would be if I relay a 4-second video segment to one of the peers out in the crowd right now, there's a micro payment that's appended to it, which is on the order of 0.00001 cents or dollars, right? So too small to be denominated by traditional fiat currencies, but over the course of earning a couple of days or weeks or months, then the amount of tokens that you accrue really becomes substantial. And then you have a number of these monetization models that I mentioned earlier, those things become possible now. So that's the basic structure for Theta, these two layers. So speaking about the mesh streaming and the data delivery layer right now, I think it's important to preface it by saying that peer-to-peer delivery of media content is not new. I'll be the first to tell you that. 20 years ago you had Napster, you had Kazaa, I'm sure there's various implementations of that in the free market also, and you have BitTorrent as well. But the thing with these legacy peer-to-peer models, I guess you can call them, is that they hit a number of friction points and hindrances that really prevented them from gaining wide user adoption, right? It was very niche, and sadly to say, it was adopted largely for pirating content, right? So we've taken a lot of these pain points and we have specifically addressed them through our approach. So the first thing that we've done is that we've looked at, the legacy peer-to-peer solutions, they've always required downloading a software client. And anytime you ask a user to download anything, that automatically rules out perhaps 80 to 90% of the user base, right? It's just too big of a friction point to overcome. So in our integration with a number of our enterprise partners, everything is seamless. Right when you hit the video stream, a blockchain wallet address on Theta is generated for you, even if the user is not logged in. So we're doing this by integrating with the app through an SDK of ours or through the video player itself with a few lines of JavaScript code on PC desktop web. So another thing was the incentivization models of these legacy peer-to-peer systems. You take BitTorrent, for example, a really popular mechanism was a tit-for-tat type of model, right? So you have an arrangement where if you wanted to go onto BitTorrent and say you wanted to download a movie, and it was 2 gigs of data, you had to upload 2 gigs of data in order to download the 2 gigs of data, right? So there was no outward reason for users to continue to contribute on the network. After they downloaded that movie, they shut their computer down or they take their node off of the BitTorrent network and they cease contributing. So it really relied on this altruistic tendency of the community to continue to power it, which had various levels of success. You could argue that was very niche, like I mentioned earlier. So what we've done is we've essentially turned that model upside down, where instead of a negative reinforcement model where you're punished for doing something that, or you're punished for not doing something, we're making it so that you're rewarded for doing a favorable behavior. So our mesh network depends on a plethora of nodes all around the world contributing their mobile devices, their PCs, their smart TVs, their TV set-top boxes, perhaps their small server rig that they have at home onto the network. And you can imagine that a user, once they're done watching TV or and they're ready to go to bed, they can still keep their node, whether it's a computer, whether it's a mobile phone, on and contributing to the data network overnight, and they're earning these data token rewards as they're doing it. So that's, that small paradigm shift is what we think And what's been demonstrated earlier is how we're going to really, transform this user adoption type of mentality and get mass market adoption. So, talking a little bit about the architecture of the mesh streaming network, we have 3 global caching layers, you could call them. So, at the very basic level, you have a viewer, a casual viewer that doesn't know much about crypto, doesn't know much about blockchain. So they're just watching the same video stream that they would always be watching, but at the same time, after they opt into contributing to Theta, they're able to serve that video stream that they're watching to 2, 3, 4 other peers that are concurrently watching that same stream. So that's the most casual viewer. And then we have the edge cacher layer, which is basically for power users or hardcore users that understand the technology a little bit more, they understand streaming, they understand that they would be serving as an edge server at the very edge of the network. And these ones, they dedicate perhaps some hardware to the network, and they will be able to simultaneously serve various multiple streams at the same time, up to 50 to 100 people, viewers that are watching these streams. And then the last caching layer is the legacy CDN, which I just mentioned. Our go-to-market is not to ask these enterprises to really swap out their existing infrastructure yet, right? That would be very infeasible and impractical at this point. So it's always falling back to the CDN, and so if there's no viewer and there's no edge cacher that can serve a third-party node that is requiring a certain video stream, it's always falling back to the CDN. So there's no degradation or decrease in the quality of service to these viewers. There can only be a potential upside to these viewers through earning tokens, and potential upside to these video platforms and content service providers by offloading a certain amount of bandwidth. So we're supporting a number of device platforms right now. We're on PC, mobile, TVs. We're just moving into smart TVs and TV set-top boxes. We're finding that the compute requirements for these TVs and set-top boxes is not that high for just relaying and contributing excess bandwidth. And so we're targeting the video streaming use case right now with a future vision of getting into all types of static content, advertisements, static video files, game patches, and other things of that sort. So now let's talk about the blockchain layer. So we're really taking care of 2 things right now. And let me jump ahead to a few slides. So our key focuses, right? So I'll talk about the first 2 on the left here, and then we'll get into some slides diving into the technical details. So what we're really looking to do is increase transaction throughput for a video use case. Like I mentioned, every small video segment should be batched together in some sort of way, in some sort of layer 2 solution, and then that way the blockchain doesn't get overwhelmed by these numerous high volumes of small microtransactions. Scalable distributed consensus is something that we would really like to work on, and that's something I'll talk about next. And then these last 3 on the right are basically how we're working with our enterprise partners and how we're working with our viewers so that we enable this intuitive, seamless user experience that users they may not have to understand blockchain at all, but they'll be able to reap the benefits of the token economic rewards that we're providing. So we'll get into scalable distributed consensus first, and then I'll come around and I'll talk about the rest later. So with scalable distributed consensus, I'll set the basic context here, which is that you have a large set of nodes connected through unreliable networks, and the point of it is to get to consensus on a point of truth, get to agreement. And so within this paradigm, we have this impossible triangle with throughput, decentralization, and consistency. And it's widely believed that you can only have 2, where you sacrifice a little bit more on the 3rd component. So our consensus mechanism, we're starting off with a PBFT approach. So why PBFT? PBFT has been demonstrated to be able to support excess of 1,000 TPS, and also it's been demonstrated to be able to support safety and guarantee safety even in asynchronous network states. So we'll take this PBFT approach, and the first step is to allow permissionless access. It's very basic, but it's kind of a walkthrough for how we're thinking about our multi-level BFT. So we want to allow permissionless access to every node in the network. And a vanilla implementation of PBFT doesn't quite cut this because we open the possibility of Sybil attacks, where you have one node that only has one vote. You open the possibility of a number of malicious nodes coming into the network and overwhelming these honest network nodes. So what do? There's been various implementations where you basically weight the voting power of a node based off of the amount of tokens it holds or the amount of stake that other nodes hold. Other nodes will stake to that node. So that's essentially a DPoS type of implementation. So that's great. The step 2 is now to enable more nodes to verify the blocks. And numerous chains, almost all chains, allow users to run a full node, so they can download all of the contents of the blockchain, and then they can start monitoring the state of the blockchain. The only difference is that these nodes cannot actively participate in proposing blocks, and they don't get the block rewards that are proposed from this block committee, or the block proposition committee, which is the validator committee. So in this diagram on the right, hypothetically, we have 4 validator nodes. They form the validator committee. They're proposing blocks. Our third step is our big step forward, right? This is our big innovation, which is to allow mass participation in the consensus process. And the way we do that on the diagram on the right is we still have a validator committee of these 4 validators, but we surround them with a second tier of consensus security that we're calling guardian nodes. So the guardian nodes will help to validate and vote for blocks. They'll also be rewarded for validating these blocks, and then they'll need to deposit a certain amount of stake. So what's the guardian node arrangement look like, you might ask? We're targeting, in excess of 1,000 guardian nodes. And so the logical next question that follows that is, great, it's good to have 1,000 guardian nodes to serve as a second layer of consensus that would check and verify the blocks that the validator committee proposes, but how is that actually possible, right? You have communication overhead. If you have 1,000 nodes, you might have 1 million messages being transferred throughout the network at any given time for these 1,000 guardian nodes to come to consensus. So one way that we're proposing this is to implement these checkpoint blocks. And so what I mean by checkpoint block is being able to take a certain chunk of the blockchain, and so these guardian nodes will not vote on every single block because that's the role of the validator committee. Rather, they're voting on each checkpoint block, and a chunk of these checkpoint blocks can be 100 blocks, or 50 blocks, or 200 blocks. And the reason we can do this is basically spot checking at specific intervals, regular intervals along the chain, is due to the blockchain immutability property, which is that, in the header of each block, you have the hash of the previous block. So basically, if the guardian nodes agree on one block of the checkpoint block, they basically agree on the entire blockchain up until that block, or at least the entire blockchain up until the previous checkpoint block. So essentially what we're doing is we're chunking the blockchain, and we're having the guardian nodes vote on consensus for that. What this really allows us to do is it gives sufficient amount of time for the guardian nodes to reach agreement. So you basically have a comparison here. And so this strategy basically is kind of the inception of why we're calling it a multi-level BFT solution, right? So the first level is the validator committee. Our nomenclature here is that the validator committee proposes blocks, and these blocks are called settled blocks. And then after the guardian nodes vote on the blocks, at the checkpoint blocks, all of the blocks up until that one checkpoint block become finalized blocks. And once blocks are finalized in our chain, they become irreversible and irreversible state. So a side-by-side comparison, the validator committee, they work on block settlement, the guardian network works on block finalization. There's a relatively small number of validator nodes compared to the guardian network, although I should say that the guardian network is actually a superset, right? So all the validators are actually guardian nodes as well. Validators produce new blocks at a faster speed, and basically the guardian network only finalizes the blocks at these various checkpoints. So Having said that, we've implemented this checkpoint block type of approach. Have we gotten there yet, right? Can we achieve this 1,000, this number of 1,000 Guardian nodes? With the naive implementation of an all-to-all broadcasting, messaging broadcasting, it's still very high. It's still very high complexity, right? And so it yields a quadratic communication overhead where simply it's too much for the entire network to come to consensus on, especially with 1,000 Guardian nodes. So what we're doing is basically we need to come up with a way to condense the type of messaging and the digital signatures that are being passed throughout the network so that we can allow for a larger number of participants to participate in the Guardian node consensus. So we're leveraging signature aggregation. So what this is it's basically a constant length signature that encodes the approval of multiple other Guardian nodes. And so that is, this diagram on the right shows that every Guardian node sends its own unique digital signature to the central Guardian node, and then the Guardian node collects it and then propagates it back out with a digital signature of the same length, but also with a compact bitmap of all the signers that are encoded in that bitmap as well. So one Guardian node basically collects all the digital signatures and then propagates it back out. So this communication complexity now is drastically reduced. We'll kind of walk through this animation. So now, with this simple illustration, it's still not enough because the central node might be a malicious node that would affect all the other signatures that have been propagated and compiled. So how do we guard against these malicious Guardian nodes? This is where we have the aggregated signature gossip. It's not just one Guardian node that does this. It's every Guardian node in our network that's contributing to this gossiping out of the aggregated signatures. And they're gossiped out until 2/3 majority consensus is reached. So this is basically a short type of animation where we'll walk through it really quickly. Okay, so then Byzantine node handling is basically assuming that there are some Byzantine nodes in the network. This gossip type of propagation can route around these Byzantine nodes. 12 minutes left, so our research-oriented micro payment pool is basically a layer 2 solution, taking inspiration from state channels and payment channels and basically customizing that for 2 nodes that are opening up a peer-to-peer relationship. And so they basically send these payment receipts back and forth to each other until the relationship is consummated and is closed, and then one payment receipt is sent to the blockchain for a token reward. So I want to talk a little bit more about the last 3 components. The seamless integration with existing infrastructure and this intuitive UX and design. Firstly, on this token usage, on Sliver TV, we're basically allowing our users to have a hybrid payment method, right? So you take a pair of these earphones, for example, headphones, and say it costs $300. If you have enough tokens, you can pay it all in tokens, or you can subsidize it a little bit if you just have a few tokens and you want to get maybe $20 off of it or something like that. So we're coming up with these concepts and these experiences for users to intuitively understand it, and these concepts aren't foreign to them. It's just that we have to kind of weave it into an experience that they understand. And then finally, our DApp partners, the way that we're going to market, as I mentioned earlier, is not to approach these enterprises and say, we're a decentralized blockchain, which we are, but our approach is not to go up to them and say, you should swap out your existing infrastructure and then plop data in. Our starting point, at least, we're taking a very measured approach, is to be the supplementary layer that sits on top of their existing infrastructure. So that way we can offload as much bandwidth as possible, and then this allows the users to benefit from it, and then this allows the platforms to retain and engage their users a lot more as well. I think that's about it. I just want to say thank you for coming here and listening.